So this is the first of 4 videos that we're going to look at for Physics 12 for data analysis. And each of the videos comes with a little one-page worksheet that we're going to complete and then submit and hand in, and I'll mark that for you. And I just want to give you a little introduction for how this process works, not only for the worksheets, but just in general for how scientists actually analyze data. And it turns out our method of analyzing data goes back to just graphing lines from Math 10. And we're experts at that. We know the general plan is if you set up an equation like y equals mx plus b, then the number that sits right here is going to be the slope, and there is just one number that goes there for any given graphing question. And the number that goes here would be the y-intercept, the value for y when x is 0. And then we would have this table of values, sometimes called a roster, with a whole bunch of x's and a whole bunch of y's. And then we could use those points of x's and y's to actually graph this line. And of course, in grade 10, we had our y-axis and our x-axis. And then you'd go ahead and you'd plot those points. And eventually, you'd come up with this beautiful line that's going to have a y-intercept of 3 and a slope of 4. It might end up looking something like that. We're going to play this game in reverse. We're going to be using just our skills for graphing lines as a method for trying to find some physics value. And those physics values that you're trying to determine will probably be embedded in the slope of the graph or in the y-intercept of the graph, or sometimes some combination of the two. As we go through this process, we're going to be trying to take our physics stories and rearrange the equations until they have this form. The vertical axis by itself on the left, and the horizontal axis after the equal sign in the term that would contain the slope. And then if there is a loose y-intercept, it'll be off on the side. So just before you try out that first worksheet, let's just take a look at a few more issues, like how this actually relates to the physics. So let's talk about a little physics experiment. Imagine you go to the physics store and you buy yourself a new spring, and you're wondering what the spring constant of this spring is. The value for K, right? The stiffness of the spring measured in newtons per meter. Well, the idea is it abides by Hooke's law, F equals kx, where x is how much you extend it. So once you've extended the spring out, then the spring pulls back and you're applying a force forward, and you should be able to determine what the spring constant is. Okay, some options for how you might go about doing that. Here's the worst option ever. Put all of your eggs in one basket. Do one experimental trial, one point only, one pair of x's and forces, where you could then try to find the K. You say, well, I stretched the spring by 2 meters, and the force was 14 newtons. And I'm going to divide and say, oh yeah, it's 7 newtons per meter. Well, okay, that's a good idea if you never make a mistake. If that one trial that you do is perfect. I don't know about you, but whenever I make pancakes, the first pancake that I make is usually not my best. So I don't want to just do one pancake here and hope that it's perfect and then just leave that story. I want to come up with a plan where I can, do a whole bunch of these trials and then blend the ideas together. So here's the plan. Why don't we do an experiment where we try a number of values for x and watch the values for force, respecting the fact that every one of those rows in the table is probably a little bit wrong. And then if we put it all together in a graph, we can use our graphing skills to try to come up with the right answer for K. Our goal every time is to create a picture in the physics that feels just like Math 10, where you have your vertical axis by itself on the left. We're actually going to go to the extent of circling that axis when we go and rearrange the equation, just so you can see that, yeah, it's all over there by itself. That's my up and down axis. Then, after the equal sign, you're going to find a term that contains, at the end of it, the across axis. Not at the very beginning, but at the end of the term. So it's not xm, but it's mx. And there's my across axis. And when I do that, the number in front of the across axis will be the slope of the graph. And if there is anything loose hanging on the end, that'll be the y-intercept. So that was great for, some sort of Math 10 story where I could say, yeah, here's my vertical axis, and there's my horizontal axis. Well, great, let's move on to some physics. How about this? How about we look at this and say, well, my force is all by itself on the left over here. It could be my vertical axis, and the extension of the spring, that could be my horizontal axis. I know those are going to be the axes in this story because look, I have all of these values for x and for f. And just like in Math 10, when you had a whole bunch of values for x and y for any one line you were drawing, those were your axes, right? The x and y axis. And then the slope and the y-intercept were some constant numbers. So when I go and do this graph with the physics, I'm going to put my force numbers up and down. I'm going to put my extension numbers across. And then I'm just going to go and plot every one of these points, right? So I'd say, oh, okay, well, 1 over, 7.5 up. Okay, great. So 1 over 7.5 up, maybe that's here. And then my next point was 3 over 24.5 up. Okay, it might be around here. And then the last one was 6 over, and it was 49 up. Now you have to respect the fact that every one of those points, because they're an experimental trial, every one is potentially wrong. There's some experimental uncertainty there, and that's okay. We can then take a ruler, we can take our eye, which is this fabulous instrument for looking at the story and saying, you know what, I think that's the best fitting line. And your best fitting line will quite likely miss every single one of your data points. That's okay. We're going to go with the average, with that best fitting line. And when we find the slope of that line, okay, so we'll pick a couple of points on this line. We will never use the data points to find the slope because they were all wrong, right? So I wouldn't use those black data points, but I would use these green points here and I would figure out the slope of this graph, right? That'd be something I'd be wondering about. And the slope would actually represent this spring constant. Okay, the number I get, I'll write it down to 2 or 3 sig figs, get the units right, and that'll be my newtons per meter number for this story. That's our plan, and it's way more powerful than just doing one trial, where you might be making a horrible mistake on that one trial. All right, a couple of other little issues, things that you're going to see happen. What if the physics relationship that you're looking at isn't linear? What if it's got some stuff that's squared? Maybe you're trying to find the mass of an object and you have some ability to know the kinetic energy and how fast it's going. So that's what I've got here, right? I've got a whole bunch of values for velocity and for kinetic energy. And I might be thinking, oh, okay, well, since there are so many values for V and for E, I bet you it's going to be like this. That'll be an axis and this will be an axis. And this is a horrible idea, by the way. It doesn't work. If you put kinetic energy here and velocity there, when you try actually graphing this, it goes like this. It's not straight at all. And we're only good at analyzing things that are straight, things that are linear. So we want to come up with a different plan than working with just E and with V. And it doesn't even really have that grade 10 feeling to it, right? I want something that feels like this. Just my across, or my up and down axis, I should say, equals some sort of thing that is never changing in the story times the across axis, and maybe, if it's there, some sort of y-intercept hanging on the end. Okay, well, you can't say like, oh yeah, x and then squared, that's why it's all parabolic, but you could do this. You could say, well, how about we go and graph not v, but v squared? What if we make that our across axis? This could be our up and down axis. It's now got this feeling that looks like that. It doesn't have a y-intercept, but I've got my up and down equals a number multiplied by my across axis. And in this case, that number, that slope, would actually be all of this. So when you go and do this graph, well, for starters, you'll have to have values for v squared for your graph. So you might need an extra little column in your table where you could take all of these v values and square them. So 2 squared is 4, 3 squared is 9, 4 squared is 16, and those are the numbers that you would work with your graph, because that's the form that looks like grade 10. So you could say, oh, let's do kinetic energy, and let's do v squared. And I would work with these two columns. They're the ones that are changing so often I had to put them in a table. So that's the reason why I'm circling them in my physics relationship. And if you put those points down on the page, 416, 936, 1634. That's going to make a nice, beautiful straight line. Well, it might be pretty close to being straight. You know, there might be some experimental uncertainty in there, a little bit of error here and there. So you draw in a best fitting line. And then once you've drawn that line in, never look back at those points. Okay, the 416, 936. Pick some points on your line, nicely widely spaced if you can. Find the slope. So that comes right off of your graph experimentally, and the slope would be half the mass of the item. So if you were trying to find the mass of the item, hey, find the slope, and then that's equal to half the mass. You could just double your slope and you'd know what the mass is. Okay, let's look at a few other little issues before we look at the homework. Fractions are fine too. Maybe you've got some physics relationship that looks like this, right? Just one that I've made up, kind of some weird looking equation. And it looks like in this experiment, people are changing G and they're changing W. So I might look and go, okay, well, they're changing G and they're changing W. Well, that doesn't feel at all like grade 10. That doesn't look like this, you know, where it's equals something constant multiplied by the across axis. So I'd have to rearrange that, right? That's no good. But how about this? Couldn't you rearrange this equation as W is equal to maybe 4 pi f multiplied by 1 over g squared? That now could have the feeling that looks like this. It wouldn't have a y-intercept, but it's got that slope multiplied by the across axis feeling if I make this my across axis. And that could be my vertical axis. So when we go to rearrange equations, the expectation on you for this set of assignment questions, right, these 4 pages, is that when it says to rearrange the equation, that you'll actually circle the axes and say, all right, there they are. Those are my vertical and horizontal axes. In this case, I guess you would need to go and make a little courtesy column calculation here of 1 over g squared values, you know, like 1 over 2 squareds, 1 over a quarter, you know, that's like 0.25. 1 over 3 squared, 1 over 9, you know, like 0.11. And then 1 over 4 squared, you know, whatever 1 over 16 is. I'm not even sure what that looks like exactly. 0.0625. Okay, that could go here. And you would want to graph those values. And then it would go beautifully straight, right? Then it's going to have that feeling, right? That feels like y equals mx. Oops, not an m here, an x. But you would be graphing w and 1 over g squared. And if you did, it would go beautifully straight. You know, your points would go on here. There might be a little bit of experimental uncertainty to them. Don't be shocked if when you add in that best fitting line, it has the theme of the data, but it might actually miss most of them by a little bit. That's okay. That's okay. And you could find the slope right off the graph, and that slope would actually equal this thing, this 4 pi f. So if people ask you, what does the slope represent? You can say, oh, it equals 4 pi f. And if you were looking for f, once you knew what the slope was, you could just divide by 4 pi and you would know exactly what f was. Okay, a couple last issues. Y-intercepts. Look at this experiment here. What's going on? They've got Q's and W's that are changing. So many different Q's and W's that they had to put them in a table. So that's changing. And this is changing. Okay, so how could you rearrange this equation here in order to get this to work? Well, it looks like they've got, you know, W going up and down. That's the vertical axis, okay? So if this is going to be the up and down axis, you'd have to get that all by itself on the left. So I would write this maybe W equals. Now, the next part. Your goal is to make it look like grade 10. The across axis has to be in this term that's after the equal sign, but it's got to be at the back end of it. It can't be in the middle of it. So when I go to rewrite this, I don't want the Q sitting there in the middle. I want it at the back end. So the only acceptable way that we'll write this here for Penn High is we're going to say that's equal to 2V, and then multiplied by the Q. And what else would we have? Minus a K, I guess. Right? It would look like that. Now it has the right feeling to it. Got my axes, my x-axis, my y-axis, if you want to call them that, right? My up and down axis and my across axis. And now I could go and actually graph this. And what I would find, this one's probably going to have some sort of negative y-intercept to it. If I was to actually go and graph it, it might go, let's see if it would have a y. Yeah, it'll be close. So it might look something like that, with a little bit of a negative y-intercept. And if you were to go and find the slope off of this graph, the slope would equal 2v. So in this experiment, whatever v is, it would be constant. And you could find its value by finding the slope of this line and then say, hey, you're equal to 2v. That's what you represent. And if you wanted to know what this k value was, well, minus k would actually be your y-intercept. So you could just look at the y-intercept of the graph, just read it off with your eye to 2 or 3 sig figs, and that would tell you what k was. All right, almost ready to go. This first lesson's kind of the biggest. Let's just look at this worksheet here for a second. This is your first one. The first few questions here in each of the 4 experiments below, you have to circle the variables that are changing, rearrange the equation, and then indicate what the slope would represent. And if there is a y-intercept, show what that would be. Sometimes there are some and sometimes there aren't. So all of these are basically the same. I'm going to show you a little sample one here in a minute. They've got the graph on the go for these first 4 here, right? Like there's your vertical axis, there's your horizontal axis. So you can start to go over here and say, okay, you are going to be the horizontal axis, you are going to be the vertical axis. This is not ready to go yet. Because if you want it to look like grade 10, then the vertical axis has to be by itself on the left. This one's not set up that way. I'm going to help you out a little bit on this first one. That A would have to be all by itself. So as you go to rearrange the equation, it's going to have to say A is equal to. Now, after the equal sign, that's where you're going to find the across axis, but it's got to be at the back end of that term. So yeah, I guess we're going to have to divide by mass. I might write this as, 1 over mass times F net. So I'm helping you out on this first question. Got my horizontal axis, got my vertical axis, done my rearranged equation. Okay, there, I guess maybe that was supposed to go like right there. Done. The slope on that story represents what? Okay, don't say, oh, it's the relationship between net force and acceleration. No, that's not the case. That's what the graph represents. The slope represents this thing that's bumped into the across axis right here. That's your slope, 1 over the mass, right? So you could put in here, hey, that's 1 over m. The y-intercept? Well, there isn't one, right? The y-intercept would be hanging off the back end. I don't see that here at all. So you can just put, nope, not applicable, there is none. Right? So that's what the first question looks like. So the next 3 go like that. And then over the page, actually, I probably should have said there are 6 of them here. 5 and 6 continue on with the same plan. I want to give you a little advice, though, on 5 and 6 and maybe on 3 and 4 as well. So here I made one up, just so you can see what this looks like. So here's some crazy equation I've just made up out of nowhere. So just last little bit of advice here. Let's say you're doing some experiment and it's performed where you have maybe, maybe a constant, let's make it a constant W and a constant, what else could we have? M, but maybe a changing P and a changing R, right? If that's what they said in the story, there might be a little table here with P's and R's. And you could go, oh, okay, well, how could I get this to work? That's changing. So circle the changing things. That's changing. Oh, okay. Hey, if that was the story, I could rewrite this as P is equal to. Now here comes all the constant stuff. Stuff that wouldn't be changing in this story. There, that's a nice rearranged equation. And this is what scientists would do if they wanted to try to find a value for this 4 pi squared w cubed all on top of m squared, they would do an experiment where they would change the r and the p, and then they would go and graph. And they would say, all right, why don't we put p up and down, we'll put r across, we'll get a straight line, and then the slope would represent all of this stuff that's not circled. It would be 4 pi squared w cubed all on top of m squared. It doesn't have a y-intercept, right? It's like plus 0, so none. Right? That's the plan. But what if we change it a little bit? Right? Let's just redo this. Let's try this again. What if the story says, oh, no, we're going to have changing p, but maybe also a changing m. Okay, so maybe that's changing. But maybe the r isn't. Oh, okay, well, we'd have to recircle stuff here. I guess that means this is changing. So how do we address that? How do we make that feel like grade 10? Because that doesn't look like grade 10 right now. And your table would have some m's up here. Well, we could rewrite it like this. Right? We're just going to use our algebra skills. You could say p is equal to, okay, I don't want to put the m in, so 4 pi squared r w cubed, that actually didn't need to be up so high. Let's drag this down a bit, and then multiplied by, because it's got to be multiplied in grade 10, I'd have to write that as 1 over m squared. That would have to be my across axis. And that could be my up and down axis. And so my graph, yeah, it would have down here 1 over m squared, just like that. And then what does the slope represent? Well, all this stuff right here, 4 pi squared r w cubed. And in any experiment like this, all of that green stuff would not be changing. So you could go and use the graph, find the slope, average out all those points that have a little bit of a problem to them, right? They might be missing the line a little bit. You could find the slope off this graph with your eye or with a computer and then say, hey, that's equal to this. And then you could solve for maybe the r or the w. So hopefully you know the other one of the two. There is no y-intercept in this one because there's nothing hanging off the end of this formula, so that would be a none. So that's how the first 6 questions go. And then the last one. Okay, this last one here, little story about a car that's accelerating. It does have an initial velocity. You can kind of see that kind of shown up here in the graph. And then various final velocities at different times of the day. And so the equation is given to you here. Vf is equal to Vi plus At. And it looks like, just looking at the table, I'm going to get you started. It looks like we've got changing t and a changing Vf. Okay, well, you need to rearrange that until it feels like this. Vertical axis by itself on the left, okay, maybe you're good there, equals, and then the term that contains the across axis with the across axis at the back end of it, and then loose stuff. So you've got to do a little rewriting of the equation, not much, but just a little bit to get it to be in that form. For questions B and C, this is so important. You should not be using this table of values. You see, once those points are plotted here and here and here and here, they're all wrong by a little bit. And that best fitting line that's already been added in for you, it is better than those points. So do not ever go back to the data table to calculate a slope. If you do, it's wrong. Okay, there's no way around it. If you do, it's wrong. You won't receive full credit for that. Instead, you want to be calculating the slope right off of this line, like maybe from that point up to, I don't know, this point here, and use those with a little slope triangle to figure out what the slope of that best fitting line is. And that'll be something that helps you find the acceleration. And the initial velocity, you know, if you're ever peeling off a y-intercept, just use your eye and give an answer to 2 or 3 significant figures. Same thing if you're quoting a slope off of a graph. When you give an answer, don't write down 9 significant figures, just write down 2 or 3. And so this worksheet, we're going to hand that in. If you've got any questions, do feel free to ask. And each one of these little activities will get a little bit more involved. First day's got the longest video though, so all the rest of the videos are much shorter.